Okay, so welcome to the 7th section of CS-188. So in this section we will start with probability and Bayes nets, but before we do that, let's have a quick recap on approximate value functions. So when we compute a value function, we may have a first strategy that will be based on a tabulation of the different values of all the states. That means that we need as much storage as there are states in the environment we consider, and that may very quickly become unmanageable. So what we'll do instead is that we'll create a family of features, fi of s, and we'll weigh them, and we'll say that our approximate value will just be a linear combination of these features. So now our objective will be to find the right weights and also interesting features. And so the issue here is that so unless you have a way to learn these on the fly, which we'll do with complex approximation functions such as neural networks, for now you're stuck with having to handcraft your features, and that will mean that they will be very problem specific. So in problem 1 we'll also see that deciding on the weight will mostly depend on the problem. So we'll have a grid world but 3 different variations of it, and for each variation we will want to decide on different weight values depending on the problem we're studying. So that's one thing that could make our life simpler, because we don't have to compute a full table. However, well, we have a difficult job of finding appropriate weights and good feature functions. Also, keep in mind that here, the more features you'll have, well, the more expressive your approximation will be. However, the more weights you'll have to tune, so that can become a trade-off very quickly between the number of features you have and the number of weights you want to have to tune. So here you want to be basically parsimonious. The other thing that we're going to do today is studying Bayes nets. And before we do that, let's start with a quick recap of some probability. So in probability we generally at first manipulate what we call marginals. So it's just the probability that something takes a certain value. And then we may be interested in conditional probabilities. So for instance, the probability that b takes a certain value, lowercase b, when we know that a takes a particular value. And this will generally be encoded for the different states that b can be in and different states that a can be in as part of a conditional probability table, CPT. So why are these useful? Well, we could use another object that's called a joint probability. But the problem is that here, if we do this, we'll have a large table if we choose to consider more variables. It will need as many dimensions in my table as I have variables. So what we may want to do is decompose these tables and encode a couple and leverage a couple of assumptions we can make on our random variables. So the different assumptions we can make can be summarized as follows. So we first have independence. And so A is independent from B if for all state A, for all state B, probability in the joint is just the product of the marginals. So that's the definition of independence. We also have conditional independence, and here we'll say that A is independent from B conditionally to C if for all A, for all B, and also for all the values that C can take, we have the same property, only now the probability distribution we consider is the conditional. So here, if you, oops, actually that's a C, sorry. Here, if you consider, if you remember, sorry, that a conditional probability is also a probability distribution, you can see that we just use the independence with a probability that happens to be the conditional condition with respect to C. Now, how do we define a conditional exactly? So we'll say that the probability of A conditional to B is just the joint divided by the marginal, and this means that we can rewrite the joint as follows with the chain rule. And actually, because the joint is symmetric, we can do the same thing, and this time we condition with respect to A. And that gives us base rule. The fact that P of B knowing A is none other than the probability that is given if I know the reverse conditioning divided by a normalizer here. The last thing that you'll need to know about the probability involved in this section is how we structure Bayes nets and what they mean. So they just encode assumptions about the variables. So for example, there is independence. How do we encode that in a graphical way? Well, A independent to B will be represented by a variable A and a variable B without any connection. Now, if they are related, each of them, to other variables, well, that also applies to the other variables. C and D, here in this case, will be unconditionally independent. The other pattern we have is the parent of multiple children. So here, for example, A is the parent of B and C. This means that B is independent from C conditionally to A. That's also something you encode with the following kind of network. If A is in between C and B, I encode the very same thing. So typically you would use that to represent a Markov chain. Here, in a Markov chain, x of t plus 2 is independent from xt, conditional to xt plus 1. This means that knowing xt plus 1 entirely characterizes the probability distribution over xt plus 2. Okay, here if we know xt plus 1, that's it. We're good. We have an entire characterization of the probability distribution over the different states that xt plus 2 can be. So knowing xt here will not change anything to this probability distribution. And that's the same thing in this pattern here. If you know A, you have all you need to characterize the probability distribution over B, and information that comes from C will not change anything about that. And finally, one thing that you may want to keep in mind, so when you have independent variables that have, a common child, so we'll see in exercise that in general this will mean that if you condition with respect to C, A and B will not be independent conditionally to C. So in some cases it may actually be the case, but in general, although A and B are independent here, if you know information about C, well, you will that will imply that information about A will change the beliefs we have over different states of B. And the last thing we may want to remember when we have a Bayesian network is the adaptation of the chain rule. So this time we'll say that the probability over a family of variables, so for example A, B, C, the joint, so this will just be the probability of A conditional to the parents of A times the probability of B conditional to the parents of B times the probability of C conditionally to the parents of C. And in case there is no parents, well, in this case we will just consider the marginal, for instance if C has no parents, and in this case the marginal is also called a prior. That is to say, if we don't have any information about that are given to us by measurements or observations, that's just the prior belief we have about C. So for instance, just to give you an intuition about what this means, because it's important in Bayesian inference, you could have two variables. So say that you play the lottery and you have a variable that is whether you have the winning ticket, and you look at the ticket and you can see that whether 9 over the 10 digits are winning. Let's just say that the ticket has been one of the digits has become unreadable. So if you don't observe L, say that you only see T, you know that you have a certain latent probability of winning the lottery. Okay, that's the prior probability of winning the lottery. Now, if you know some information about your ticket, well, your beliefs over T will change. And the way you can make them change, and that we will see later in the class, is just by using Bayes' rule. So remember that P of T given L is nothing more than P of L given T times the prior divided by P of L. And here all you need to do is compute this product here. You'll know that this normalizer doesn't depend on T, so all you have to do is compute these unnormalized beliefs, which are likelihoods over the different states of T, and then you just normalize by the sum, and now you obtain a probability distribution. Okay, and this is called a posterior. So now that you've incorporated the information you have about the world, you've changed your beliefs over T.